Welcome to Milky Narratives. Find a comfortable place to rest, let your mind unwind, and allow the worries of the day to fade away. Tonight, we'll travel through the vastness of the cosmos and discover the stories hidden among the stars. Sleep well and enjoy the journey. 1. The first light that should never have existed. Before there were stars, before there were galaxies, before any planet, moon, or living creature could even imagine existing, the universe was a place where light itself seemed impossible. Imagine opening your eyes into a reality with no sunrise, no distant horizon, no shimmering constellations, and no glowing Milky Way stretching across the night. Not because everything was dark in the ordinary sense, but because there were no eyes to see, no skies to look toward, and no stars to produce the familiar light we know today. Yet somehow, out of what appeared to be endless darkness, the universe managed to create its very first light. Not the light of a star, not the light of a galaxy, something far older, something that should never have existed in a universe that had not yet learned how to shine. Tonight, we are traveling back nearly 13.8 billion years, farther than any telescope can truly observe directly, into an age so ancient that even time itself seemed to move differently. We will witness a chapter of cosmic history that lasted only moments in comparison with everything that followed, yet determined the fate of every galaxy, every black hole, every planet, and ultimately every human being who would one day wonder where all of this began. It is a story that begins not with brilliant explosions lighting up the heavens, as movies often portray, but with a strange and almost unimaginable simplicity. For a surprisingly long time, the universe was not filled with stars at all. Instead, it was a vast ocean of invisible particles, expanding relentlessly into emptiness. Temperatures were so extreme that atoms could not survive. Space itself was still settling after the unimaginable violence of the Big Bang. Everywhere you looked, if looking had been possible, matter and radiation collided endlessly in a brilliant but imprisoned sea of energy. Ironically, the newborn universe was filled with light, yet no light could actually travel freely. Every photon was trapped, constantly scattering from one charged particle to another, unable to escape for more than a tiny fraction of a second. It was like trying to shine a flashlight through an impossibly dense fog, except this fog stretched across the entire observable universe. For hundreds of thousands of years, the cosmos remained imprisoned inside its own brilliance. Then, something remarkable happened. As the universe continued expanding, it slowly cooled, not dramatically in a single instant, but patiently, almost imperceptibly, over countless generations of cosmic time. Eventually, temperatures dropped enough for electrons and protons to combine into the first stable hydrogen atoms. This quiet transformation changed everything. Almost overnight, at least by cosmic standards, the dense fog vanished. The prison opened. Photons that had spent hundreds of thousands of years trapped inside the young universe suddenly found themselves free to travel in every direction. For the first time since the beginning of existence, light could move across space without constantly crashing into matter. The universe became transparent. Those ancient photons never stopped traveling. Even now, billions of years later, some of them are still crossing the cosmos. A tiny fraction eventually reaches Earth, where extraordinarily sensitive instruments can detect their faint whisper. What scientists call the cosmic microwave background is, in many ways, the oldest light we can ever hope to see. It is not simply ancient, it is the surviving echo of the universe's first successful attempt to illuminate itself. Without those escaping photons, the universe would have remained hidden forever. Without that first release of light, galaxies could never have grown into the magnificent spirals and giant clusters we observe today. Without it, stars, including our own sun, would never have formed. And without stars, the heavier elements needed for planets, oceans, and life itself would never have existed. Everything we know traces its origins back to this extraordinary moment when darkness finally surrendered. Perhaps the most astonishing part of the story is how ordinary the process appears when viewed through the laws of physics. There was no cosmic switch flipped by some mysterious force, no dramatic burst announcing that the age of darkness had ended. Instead, the universe simply expanded. temperature slowly fell. Particles naturally settled into more stable arrangements. And from those quiet changes emerged one of the greatest turning points in cosmic history. It is a reminder that some of the universe's most profound transformations happen almost silently. Long before the first star ignited, long before galaxies painted the heavens, the cosmos had already written the opening sentence of its story. It did so with a light that, against all intuition, managed to escape absolute darkness, and has been traveling ever since, carrying with it the oldest message the universe has ever sent. 2. The invisible ocean holding every galaxy together. Before the first stars ever lit the heavens, the universe had already accomplished something extraordinary. It had learned how to let light travel. The ancient photons released during that quiet transformation have been crossing space for nearly 13.8 billion years, carrying with them the earliest memories of existence itself. They remind us that the cosmos was never truly empty. Even in its earliest moments, unseen forces were already shaping everything that was yet to come. But light was only the beginning. As the universe continued expanding, another mystery quietly revealed itself. One so strange that even today, despite all our telescopes and satellites, we still cannot see it directly. Everything that shines in the night sky, every star, every glowing nebula, every elegant spiral galaxy, is floating inside an invisible ocean. Not an ocean of water, not gas, not light, but something that has never reflected a single photon. Something that has never been photographed. And yet, without it, the universe we know could never have existed. If you could somehow step outside the visible cosmos and look upon the universe from an impossible distance, you might expect to see galaxies scattered like islands across a vast sea of empty space. Instead, you would witness something entirely different. You would see enormous webs stretching across billions of light years, connecting galaxy clusters with delicate filaments that resemble the threads of an unimaginably vast spider's web. These structures are so enormous that light itself needs hundreds of millions of years to cross them. Yet the threads themselves remain invisible. What astronomers call the cosmic web is among the largest known structures in existence, and astonishingly, much of it is built upon something that cannot be seen at all: dark matter. The name sounds mysterious, almost poetic, but in reality it reflects our ignorance more than our understanding. It is called dark not because it is black, but because it neither emits nor absorbs light. No telescope can observe it directly. No human eye could ever see it, no matter how powerful it became. And yet its gravity quietly dominates the architecture of the cosmos. In fact, everything familiar, the stars, planets, galaxies, and even ourselves, accounts for only a surprisingly small fraction of all the matter in the universe. The overwhelming majority exists beyond our senses, silently influencing every visible object through gravity alone. Imagine watching leaves swirling across the surface of a pond. You cannot see the underwater currents, but by observing the movement of the leaves, you immediately know something beneath the surface is guiding them. Astronomers discovered dark matter in much the same way. When they measured how galaxies rotated, the numbers simply refused to make sense. Stars near the outer edges of galaxies were moving far faster than gravity from visible matter alone could possibly allow. According to everything scientists understood about gravity, those galaxies should have flown apart billions of years ago. Instead, they remained beautifully intact. Something unseen was holding them together. At first, many believed the calculations must be wrong. Perhaps telescopes were missing enormous clouds of ordinary gas. Perhaps gravity behaved differently over great distances. But observation after observation told the same story. Invisible mass surrounded every galaxy like an enormous halo, extending far beyond the glowing stars themselves. Without this hidden framework, galaxies would unravel like pinwheels spinning too quickly. Our own Milky Way owes its graceful spiral shape not only to the stars we admire, but also to an invisible structure reaching far beyond what any telescope can photograph. It is a strange thought. When you look at the Milky Way on a clear night, you are actually seeing only the brightest decoration on a much larger cosmic sculpture. Most of the sculpture remains forever hidden. Even more remarkable is what happened long before galaxies existed. Remember that, after the universe became transparent, matter was spread almost uniformly across space. Tiny differences in density, so small they were nearly impossible to imagine, became critically important. Some regions contained just a little more matter than others. Those slightly denser regions possessed slightly stronger gravity. And gravity is patient. It does not rush. Over millions of years, it quietly pulled more material inward. The denser regions became denser still, like snow gathering into larger and larger drifts during a gentle winter storm. Invisible clumps slowly grew throughout the expanding universe. Dark matter was the first to gather. Because it barely interacted with radiation, it could begin collapsing long before ordinary matter was ready. It formed immense gravitational scaffolds stretching across the young cosmos. Only later did ordinary hydrogen gas begin falling into these invisible wells, collecting where gravity had already prepared a home. Without those hidden foundations, the gas might never have condensed enough to ignite the first stars. In a sense, dark matter became the universe's silent architect. It built the framework. Ordinary matter merely decorated it. Every brilliant galaxy we admire today may simply be glowing paint applied to an invisible cosmic skeleton. Even modern supercomputers reveal this astonishing picture. When scientists simulate a universe without dark matter, galaxies struggle to form at all. Matter remains too diffuse, too scattered, too disorganized. The elegant spirals and giant elliptical galaxies that fill our telescopes simply fail to appear. But when dark matter is added back into the calculations, something magical happens. The simulations begin producing a universe remarkably similar to our own. Filaments emerge, clusters grow, galaxies blossom where invisible gravity has patiently prepared the stage. It is almost as though the cosmos spent hundreds of millions of years constructing an enormous invisible city before turning on a single light. Perhaps that is why the night sky feels so harmonious. Its beauty is supported by something we will never directly witness. Every star hanging above us depends upon a foundation hidden beyond human perception. And perhaps there is something quietly humbling in that realization. For thousands of years, humanity believed that seeing was understanding. If something could not be observed, perhaps it did not exist. The universe, however, continues teaching us a gentler lesson. Reality is often far larger than our senses allow. Some of the greatest forces shaping existence leave no visible trace. They ask not to be seen, but to be inferred through their quiet influence. As our journey continues, these invisible structures will begin gathering ever more gas into their immense gravitational embrace. Within those hidden cradles, pressure will slowly rise, temperatures will climb, and after hundreds of millions of years of cosmic silence, the universe will finally learn one of its greatest creations. It will ignite its very first stars. 3. The day the universe learned to build stars. Before the universe could paint the night sky with countless stars, it first needed an invisible foundation. Dark matter had spent hundreds of millions of years quietly weaving its enormous gravitational web, gathering ordinary hydrogen into vast clouds that drifted through the expanding cosmos. Those hidden structures acted like giant bowls, collecting more and more gas until gravity slowly gained the upper hand. Everything was finally in place. The universe had learned how to release light. It had built an invisible framework to hold galaxies together. Now, for the first time, it stood on the edge of creating something entirely new, something that would transform a silent cosmos into a universe filled with brilliance. For millions of years, the cosmos remained quiet until gravity discovered how to ignite its very first suns. It is tempting to imagine that the first stars appeared suddenly, like fireworks exploding across an empty sky. But the universe rarely works in dramatic leaps. Instead, it prefers patience. Gravity is perhaps the most patient force of all. Unlike explosions or lightning, gravity never grows tired. It does not need fuel. It simply pulls, gently but relentlessly, year after year, century after century, million after million of years. At first, the enormous clouds of hydrogen seemed almost motionless. Each atom drifted through space at incredible speeds, yet the clouds themselves changed so slowly that nothing appeared to happen. If you could somehow watch them with your own eyes, thousands of human lifetimes might pass before you noticed even the slightest difference. Yet gravity never stopped working. Every tiny movement inward strengthened its pull. Every atom that joined the growing cloud added just a little more mass. And more mass meant stronger gravity. It was a quiet cycle that fed itself. The denser the cloud became, the faster it collapsed. The faster it collapsed, the hotter it grew. Eventually, the center of these enormous clouds reached temperatures beyond anything we experience on Earth, millions of degrees. Pressure became almost unimaginable. Hydrogen atoms, once drifting peacefully through the darkness, found themselves squeezed closer and closer together. Nature was approaching a threshold it had never crossed before. Then, the impossible happened. Two tiny hydrogen nuclei collided with such tremendous energy that they no longer bounced apart. Instead, they fused. In that instant, a small fraction of their mass vanished. It did not disappear without a trace. It became pure energy. A tiny flash. The first successful spark of nuclear fusion. One reaction became two. Two became thousands. Thousands became trillions upon trillions every second. Almost instantly, the collapsing cloud found itself pushing back against gravity with an entirely new force. Light, heat, radiation. The first true star had been born. It is difficult to overstate how extraordinary this moment was. For hundreds of millions of years, the universe had known only cooling, expansion, silence, darkness. Now, for the very first time, there was a permanent source of light. Not ancient photons escaping from the Big Bang, not fading echoes of creation, but brand new light, continuously forged deep inside a living star. The universe had learned how to manufacture sunlight. The first generation of stars, often called population 3 stars, were unlike anything we see today. Because the young universe contained almost nothing except hydrogen and helium, these pioneers grew to astonishing sizes. Some may have contained hundreds of times the mass of our own sun. They burned unimaginably hot, brighter than entire modern star clusters. Yet despite their enormous size, they lived surprisingly short lives. Like candles burning from both ends, they consumed their nuclear fuel with incredible speed. Many survived only a few million years. Compared to our sun, which will shine for roughly 10 billion years, the first stars lived only brief, brilliant moments. But those moments changed everything forever. Inside their blazing cores, nuclear fusion continued creating new elements. Hydrogen became helium. Helium became carbon. Carbon became oxygen, then neon, magnesium, silicon, eventually in the largest stars, even iron. For the first time in cosmic history, the universe was creating the ingredients needed for planets, oceans, mountains, and eventually, living creatures. Every atom of oxygen you breathe, every atom of calcium inside your bones, every atom of iron flowing through your blood, none of them existed before stars learned how to forge them. In a very real sense, the first stars became the universe's earliest factories. They were not simply producing light, they were manufacturing the building blocks of future worlds. And when their brief lives came to an end, they refused to disappear quietly. Unable to support their own enormous weight, many collapsed under gravity before exploding in spectacular supernovae. These explosions scattered their newly forged elements across surrounding space. Clouds once made almost entirely of hydrogen now became enriched with heavier atoms. The ashes of one generation became the raw materials for the next. Future stars formed from richer clouds. Around those younger stars, rocky planets eventually began to emerge. Some of those planets would one day possess oceans, atmospheres, continents, perhaps even life. Looking back, it is astonishing how much depended on gravity's quiet persistence. Gravity never intended to create beauty, it simply gathered matter together. Yet from that simple action emerged stars. From stars came chemistry. From chemistry came planets. And from planets came observers capable of wondering how it all began. There is something deeply comforting about this story. The universe did not rush toward complexity. It reached it through countless small steps, each building upon the last. Invisible gravity created invisible halos. Those halos gathered invisible gas. The gas ignited invisible reactions inside newborn stars. Only then did visible light finally spread across the cosmos in overwhelming abundance. The silent universe had found its voice. Every star that fills our night sky today is a distant descendant of those first ancient suns. Although they vanished billions of years ago, their legacy still shines around us. Our own sun belongs to a much younger generation, born from clouds already enriched by countless earlier stars. Without those forgotten pioneers, Earth could never have existed. Neither could we. The story of humanity, it turns out, began long before our planet formed. It began on the day the universe first learned how to build stars. And as those first brilliant lights multiplied across the darkness, they did more than illuminate the cosmos. Together, they began gathering into something even grander. Vast islands of stars that would slowly grow, collide, and evolve into the magnificent galaxies that define the universe we know today. If these quiet journeys through the universe help you unwind, consider subscribing so we can continue exploring the deepest mysteries of existence together. 4. The galaxies that grew by devouring others. The first stars had finally broken the universe's long silence. For hundreds of millions of years, isolated points of light appeared across the darkness, each one forging the elements that would one day become planets, oceans, mountains, and living creatures. Their brief but brilliant lives transformed the young cosmos, filling space with heavier atoms that had never existed before. Yet stars alone were not enough. The universe was preparing something even grander. Individual stars would gather into enormous families. Those families would become galaxies, and over billions of years, the greatest galaxies would not grow peacefully. They would become giants by consuming one another. The most beautiful galaxies in the night sky became giants through billions of years of cosmic collisions. When we look up on a clear evening, galaxies appear calm. Graceful spiral arms curve elegantly around glowing centers. Elliptical galaxies float through space like enormous golden lanterns. Everything about them suggests stillness. But this peaceful appearance is one of the greatest illusions in the universe. Galaxies are constantly moving. Each one races through space at hundreds of kilometers every second, pulled by the gravity of countless neighboring galaxies and enormous clusters scattered across the cosmic web. The distances between them are so vast that these motions unfold almost too slowly for the human mind to appreciate. If you could watch the universe in fast forward, millions of years would pass like seconds. Galaxies would drift across space like enormous schools of fish. Some would pass one another quietly. Others would begin long gravitational dances lasting billions of years. Eventually, many would collide. At first, the idea sounds unimaginably violent. After all, galaxies contain hundreds of billions of stars. Surely such a collision would produce catastrophic destruction. Surprisingly, almost the opposite is true. Although galaxies themselves are unimaginably large, stars are separated by enormous distances. If our sun were the size of a marble, the nearest neighboring star would still be hundreds of kilometers away. Even during a galactic collision, individual stars almost never strike one another directly. Instead, gravity performs a much more elegant choreography. As two galaxies approach, their invisible halos of dark matter meet first. Those enormous gravitational envelopes begin pulling on one another long before the visible stars overlap. Slowly, each galaxy starts to lose its original shape. Spiral arms stretch outward like ribbons caught in a gentle current. Streams of stars are pulled into graceful arcs, extending hundreds of thousands of light years into space. Entire clusters change direction. Clouds of gas compress. The galaxies seem almost alive, twisting and reaching toward one another in a slow-motion embrace. This dance may continue for hundreds of millions or even billions of years. Again and again, the galaxies pass through each other. Gravity steals energy from their motion. Each encounter slows them slightly. Eventually, they can no longer escape one another. They merge, not with a sudden explosion, but through an extraordinarily patient process of cosmic blending. Their stars intermingle, their dark matter halos unite. Their enormous reservoirs of gas collapse toward the center, and something remarkable begins to happen. Where vast clouds of hydrogen collide, gravity suddenly finds fresh material to work with. The gas becomes denser, pressure rises. New generations of stars ignite at astonishing rates. Some merging galaxies become true stellar nurseries, producing thousands of new stars where previously only a handful formed each year. Ironically, destruction becomes creation. A collision that tears galaxies apart also gives birth to countless new suns. The universe has an extraordinary habit of transforming endings into beginnings. Even the supermassive black holes hiding at the centers of these galaxies eventually find one another. Each galaxy carries its own invisible giant, a black hole containing millions or even billions of times the mass of our Sun. As the galaxies merge, those black holes slowly spiral closer together. For millions of years, they orbit one another in darkness, gradually losing energy through interactions with surrounding stars, and ultimately through tiny ripples in space-time itself. Eventually, they collide. The merger releases an unimaginable burst of gravitational waves, sending tiny distortions racing across the universe at the speed of light. Long after the galaxies themselves have settled into a single larger system, those ripples continue their silent journey across the cosmos. Perhaps billions of years later, an advanced civilization somewhere else will detect them and realize that two ancient galaxies became one. Our own galaxy is no exception. The Milky Way has spent most of its life growing this way. Astronomers now know that it has absorbed dozens, perhaps hundreds of smaller galaxies over billions of years. Some of their stars still travel through our galaxy today, carrying chemical fingerprints that reveal they were born somewhere entirely different. They are immigrants from galaxies that no longer exist. Even now, faint streams of stars arc around the Milky Way like ancient ghosts. These stellar rivers are the last visible remains of smaller galaxies slowly torn apart by our galaxy's immense gravity. Every one of them tells the same quiet story. Nothing in the universe remains isolated forever. Gravity always brings neighbors together. One of the Milky Way's current meals is the Sagittarius dwarf galaxy, a tiny companion that has been orbiting us for billions of years. Each time it passes through the Milky Way, enormous tidal forces pull more of its stars away. Eventually, almost nothing of the original galaxy will remain. Its stars will simply become part of ours. Its identity will disappear, but its matter will live on. The universe rarely wastes anything. Perhaps the most astonishing realization is that our own sun may owe its existence to one of these ancient mergers. Long before Earth formed, one or more galactic collisions may have compressed giant clouds of gas inside the Milky Way, triggering waves of star formation. Among those newborn stars was a modest yellow star that would eventually become our sun. If those ancient galaxies had never collided, our solar system might never have existed. Neither would we. The very atoms inside our bodies may have once belonged to stars born in galaxies that disappeared billions of years before Earth formed. It is a beautiful reminder that identity in the universe is wonderfully fluid. Galaxies are not permanent structures. They grow, they evolve, they consume, they merge. And through those transformations, they create entirely new possibilities. Perhaps nowhere is this lesson more meaningful than when we look toward the future. Far from being finished, the Milky Way is still moving. Across nearly 2.5 million light-years of space, another magnificent spiral galaxy is slowly approaching. The Andromeda Galaxy is racing toward us at over 100 kilometers every second. It has been traveling this path for billions of years. In roughly 4 to 5 billion years, the long dance will finally begin. Neither galaxy will survive unchanged. Both will lose their familiar spiral shapes. Together, they will gradually merge into a single enormous galaxy, larger and richer than either one alone. If anyone is there to witness the night sky during that distant future, they will see a spectacle unlike anything humanity has ever imagined. And at the heart of that magnificent new galaxy, another hidden actor will quietly take command. For while galaxies may appear to be ruled by their countless stars, their true masters have been waiting patiently in the darkness all along. At the center of nearly every great galaxy lies an object so mysterious, so powerful, and so paradoxical that it seems capable of both destroying galaxies and helping create them. 5. The black holes that became the architects of galaxies. The future collision between the Milky Way and Andromeda reminds us of a remarkable truth about the universe. Nothing truly grows alone. Galaxies merge, stars are recycled, invisible dark matter provides the foundation. Gravity patiently guides every step. Yet hidden within nearly every large galaxy lies another presence, one so mysterious that for decades astronomers believed it could only bring destruction. At the center of our own Milky Way, buried beneath billions of stars and vast clouds of glowing gas, resides an object that never shines. It cannot be seen directly. It traps everything that wanders too close. Not even light can escape its grasp. For generations, black holes were imagined as the villains of the cosmos, endless mouths swallowing anything unfortunate enough to cross their path. Cosmic monsters consuming stars, gas, and even time itself. But as scientists looked deeper into the universe, an astonishing possibility slowly emerged. Perhaps these feared destroyers had been quietly building galaxies all along. The universe's greatest destroyers may have secretly been its greatest creators all along. It seems almost impossible. How could something famous for consuming matter also help create the magnificent galaxies we admire? The answer begins with a simple misunderstanding. Black holes are often imagined as giant cosmic vacuum cleaners, pulling everything nearby into oblivion. In reality, that is not how gravity works. If our own sun were magically replaced by a black hole of exactly the same mass, Earth's orbit would barely change. We would continue circling exactly as before. The only difference would be the disappearance of sunlight. Gravity depends on mass, not on whether that mass belongs to a glowing star or a black hole. Most black holes simply sit quietly, influencing their surroundings through gravity like any other massive object. Only when matter falls toward them does something extraordinary happen. As gas spirals inward, it cannot plunge directly into the black hole. Instead, it forms an enormous rotating disk. Friction between countless particles heats this disk to astonishing temperatures, millions of degrees, hotter than the surface of any ordinary star. Before disappearing forever, the gas shines with unbelievable brilliance. Ironically, one of the darkest objects in existence can become one of the brightest. Some supermassive black holes produce enough energy to outshine every star in their entire galaxy combined. These dazzling objects, known as quasars, can be seen across billions of light years. Their light began traveling toward Earth long before our own planet even existed. Yet brightness alone does not explain how black holes shape galaxies. The true mystery lies in what happens next. As enormous quantities of matter fall inward, not all of it crosses the event horizon. A surprising fraction is violently redirected. Powerful magnetic fields twist around the spinning black hole, launching colossal jets of energy outward from its poles. These jets travel at nearly the speed of light. They stretch for hundreds of thousands, sometimes even millions of light years into surrounding space. Imagine an object smaller than our solar system, influencing regions larger than entire galaxies. The scale is almost impossible to comprehend. For many years, astronomers assumed these jets were simply destructive. Surely blasts of such incredible power could only tear galaxies apart. But nature often prefers balance over extremes. Sometimes those jets do disperse enormous clouds of gas, preventing new stars from forming. In other regions, however, they compress surrounding material, squeezing giant clouds until gravity gains the upper hand once again. The very energy capable of halting star formation can also trigger it. It depends entirely on where that energy is deposited. In this way, black holes behave less like mindless destroyers and more like cosmic gardeners. They prune, they regulate, they shape. They determine where galaxies continue growing and where growth must temporarily stop. Without this delicate balance, galaxies might have evolved very differently. Consider what would happen if nothing limited star formation. Every cloud of gas would eventually collapse into new stars. Galaxies would burn through their fuel astonishingly quickly. Within a relatively short cosmic time, they would exhaust the very material needed to produce future generations of stars. Instead, many galaxies continue forming stars for billions upon billions of years. Black holes appear to help regulate this process, ensuring that galaxies do not consume themselves too rapidly. In an unexpected way, restraint becomes a form of creation. By preventing too many stars from forming at once, black holes preserve enough gas for countless future generations. Even more astonishing is the relationship between galaxies and the black holes they contain. Astronomers have discovered a remarkable pattern. The larger a galaxy's central bulge becomes, the larger its central black hole tends to be. The two seem to grow together, almost as though they are engaged in an ancient conversation stretching back billions of years. Neither appears to evolve independently. Each influences the other. This relationship remains one of modern astronomy's greatest puzzles. Did galaxies create black holes? Or did black holes guide the formation of galaxies from the very beginning? Perhaps both happened simultaneously, like two dancers moving so perfectly together that neither could say who led the first step. Even our own Milky Way carries evidence of this partnership. At its center lies Sagittarius A star, a supermassive black hole containing roughly 4 million times the mass of our Sun. Compared with the giant monsters powering distant quasars, it is surprisingly quiet today. It feeds only occasionally, patiently waiting as small clouds of gas drift inward. Yet evidence suggests that millions of years ago, Sagittarius A star was far more active. Enormous bubbles of energetic particles still extend above and below our galaxy, reaching tens of thousands of light years into space. These structures, known as the Fermi bubbles, may be the lingering fingerprints of an ancient outburst. Our own galaxy remembers a time when its central black hole briefly awakened. Fortunately for us, the Earth formed long after those dramatic events had subsided. Still, it is remarkable to think that the peaceful galaxy we inhabit was once shaped by forces almost beyond imagination. Perhaps the most beautiful lesson hidden within black holes is that appearances can be deeply misleading. From a distance, they seem to represent only endings. Matter disappears. Light vanishes. Nothing returns. Yet on much larger scales, they help determine where stars are born, how galaxies evolve, and how the universe maintains its delicate balance between growth and exhaustion. Sometimes creation requires destruction. Sometimes order emerges from chaos. The universe seems remarkably comfortable holding both truths at once. And black holes are not the only objects living under such relentless pressure. Every star, from the smallest red dwarf to the brightest blue giant, carries within itself another quiet certainty. The very moment a star ignites, it also begins an invisible countdown. No matter how brilliant it shines, no matter how long it survives, every star is slowly using the fuel that gives it life. Even our own sun has been counting down since the day it was born. 6. The day every star began running out of time. Every sunrise in the universe comes with an invisible sunset. The instant gravity finally wins its ancient battle against a cloud of drifting hydrogen, the newborn star takes its very first breath. Deep within its core, temperatures climb beyond 15 million degrees. Pressure becomes so immense that individual hydrogen atoms, tiny building blocks scattered throughout the cosmos since the birth of the universe, can no longer remain separate. They fuse together. In that unimaginably hot furnace, 4 hydrogen nuclei become 1 helium nucleus. A tiny fraction of their mass disappears, not because it is destroyed, but because it has transformed into pure energy. Albert Einstein described this elegant exchange with a simple equation: E equals mc squared. Every ray of sunlight that has ever touched your face began with one of these tiny disappearances. Mass becoming light, matter becoming warmth, existence becoming radiance. This remarkable process is called nuclear fusion, and it is one of nature's most efficient engines. It powers every ordinary star in the night sky. It warms distant planets. It creates the light that eventually reaches curious civilizations, capable of wondering where that light first began. For a brief moment in cosmic history, a newborn star seems almost immortal. It has achieved a delicate balance. Gravity relentlessly pulls inward, trying to compress the star into something ever smaller. Fusion pushes outward with equal determination, releasing unimaginable amounts of energy from the core. These two opposing forces create a perfect equilibrium. Astronomers call this hydrostatic equilibrium. It is less like a rigid structure and more like a dancer balancing effortlessly on a narrow beam. As long as gravity and fusion remain evenly matched, the star shines peacefully, sometimes for millions of years, sometimes for billions, occasionally for trillions. Yet even during these quiet ages, something irreversible is happening. Every second, the star consumes a portion of its fuel. The countdown has already begun. Imagine lighting a candle in a dark room. The flame appears calm, steady, comforting. Yet from the very first flicker, the candle is becoming shorter. Its ending is written into its beginning. Stars are much the same. Their brilliance hides an invisible clock. Our own sun has been burning for approximately 4.5 billion years. That number feels almost impossible to imagine. If 1 second represented a single year, the sun's current age would stretch for more than 140 human lifetimes. Yet astronomers estimate it has already used nearly half of its hydrogen fuel. Without any visible change from Earth, our star quietly inches toward an ending that will not arrive for another 5 billion years. The comforting warmth we experience each morning is evidence not only of life, but also of time passing. Perhaps the greatest surprise is that larger stars do not live longer. Quite the opposite. A star 10 times more massive than the Sun possesses far more fuel. One might expect it to shine for much longer. Instead, it burns through its reserves at astonishing speed. Its immense gravity compresses the core more intensely. Fusion accelerates dramatically. Temperatures soar. Energy pours outward with breathtaking intensity. Such stars live brilliant but remarkably short lives. Some survive only 20 million years, a mere blink compared with the Sun's expected 10 billion year lifespan. In cosmic terms, they are like fireworks, spectacular, blinding, gone almost immediately. Smaller stars, however, possess extraordinary patience. Red dwarfs, the smallest true stars in the universe, burn their hydrogen with incredible efficiency. They sip their fuel rather than consuming it in great bursts. Some may continue shining for over 10 trillion years. That is nearly 1,000 times longer than the Sun. In fact, the universe itself is only about 8 billion years old. No red dwarf has ever reached the end of its natural life. Not one. Every red dwarf ever born is still shining today. Some of the faintest stars in the night sky may outlive entire galaxies. This reveals a curious lesson that extends far beyond astronomy. In the universe, longevity is not always granted to the largest or the brightest. Sometimes endurance belongs to those who burn gently. Nature seems to reward balance more often than extravagance. Meanwhile, inside every aging star, quiet changes continue unfolding. Hydrogen near the core gradually disappears. Helium slowly accumulates like ash inside a fireplace. Fusion can no longer occur in the exhausted central region. Instead, it migrates outward into a thin shell surrounding the growing helium core. The star notices. Not consciously, of course, but through physics. Gravity begins pressing harder against the inactive core. Temperatures rise once again. The outer layers respond. They swell outward, slowly, patiently, almost imperceptibly over millions of years. A familiar yellow star begins transforming into something much larger, something softer, something redder. One day, billions of years from now, our own sun will become a red giant. Its diameter may expand hundreds of times beyond its current size. Mercury will disappear. Venus almost certainly will as well. The fate of Earth remains uncertain. Some models suggest our planet will be engulfed. Others predict it may survive in a scorched orbit just beyond the sun's swollen atmosphere. Either way, the oceans will have long since vanished. The continents will become molten. The blue world we call home will no longer resemble the place where life first learned to dream. Fortunately, none of this threatens humanity today. These transformations lie so unimaginably far in the future that every mountain on Earth will have eroded away countless times before they begin. Entire species will rise and vanish. Continents will drift into unfamiliar shapes. The stars above future skies may look entirely different. Yet the sun's silent countdown continues all the same. Its clock never pauses. The same is true for every star we admire tonight. When we gaze upward, we are not simply witnessing brilliant lights suspended in darkness. We are observing countless lives unfolding simultaneously. Some stars are infants. Some have reached calm middle age. Others stand on the edge of extraordinary finales that will reshape entire regions of space. Each follows the same universal law. Birth contains the promise of growth. Growth contains the certainty of change. And change eventually becomes transformation. Perhaps this is why the night sky feels strangely comforting. The stars remind us that endings are not interruptions to the universe. They are part of its design. Nothing in the cosmos remains exactly as it was. Clouds become stars. Stars forge heavier elements. Those elements become planets. Planets give rise to oceans. Oceans nurture life. Life eventually looks back toward the heavens and wonders how it all began. The atoms within our own bodies were once hidden inside ancient stars that completed their own long countdown billions of years before the Earth existed. In a profound sense, every heartbeat carries the memory of forgotten suns. But not all stellar endings are peaceful. Some stars fade gently into silence. Others resist gravity until the very last moment. And when they finally surrender, they unleash explosions so powerful that for a brief instant, a single dying star can outshine an entire galaxy. The universe saves some of its most breathtaking creations for its final acts. 7. The worlds that could survive after every sun is gone. When we imagine the end of a star, we often imagine the end of everything around it. Without sunlight, planets should become frozen wastelands. Oceans should solidify. Atmospheres should collapse. Life, if it ever existed, should quietly disappear into the endless cold. For a long time, astronomers believed exactly that. The sun was seen as the heart of every planetary system. Take away the heart and the system itself would simply die. But the universe has a remarkable habit of refusing our simplest assumptions. As researchers explored both our own solar system and distant worlds beyond it, an unexpected possibility began to emerge. Perhaps some planets do not need a star forever. Perhaps, long after the final sunrise has faded, certain worlds may continue their silent journeys through space. Not warm, not bright, but not entirely lifeless either. To understand how this could happen, we must first leave behind the comforting image of Earth. Nearly every living thing here depends directly or indirectly upon sunlight. Plants capture solar energy through photosynthesis. Animals depend upon plants or upon creatures that feed on plants. Weather itself is powered by the uneven heating of Earth's surface. Even the gentle winds and ocean currents owe their existence to the sun. Our civilization is built upon energy that first arrived as sunlight. It feels impossible to imagine another way. Yet Earth itself quietly reminds us that sunlight is not the only source of warmth. Far beneath our feet, the planet is still hot. Its interior glows with ancient heat left over from Earth's violent formation more than 4 billion years ago. Additional warmth comes from radioactive elements slowly decaying inside the mantle. This hidden furnace powers volcanoes, earthquakes, and deep hydrothermal vents scattered across the ocean floor. Around these underwater vents, where sunlight has never reached, entire ecosystems flourish. Giant tube worms, strange shrimp, countless microscopic organisms. None rely on photosynthesis. Instead, they survive through chemosynthesis, drawing energy from chemicals rising out of Earth's interior. Life, it seems, can find another path. This discovery transformed our understanding of what a habitable world might be. Perhaps sunlight is merely one option among many. The idea grows even more fascinating when we look toward the icy moons of our own solar system. Europa, one of Jupiter's largest moons, possesses a frozen shell several kilometers thick. Its surface is colder than Antarctica by hundreds of degrees. At first glance, it appears utterly inhospitable. Yet beneath that frozen crust lies something extraordinary: a global ocean. Liquid water hidden beneath ice. Astronomers believe tidal forces generated by Jupiter's immense gravity continually flex Europa's interior. This constant stretching produces heat, enough heat to prevent the entire ocean from freezing solid. Far from the warmth of the sun, an ocean quietly survives. Saturn's moon Enceladus tells a similar story. Towering geysers erupt through cracks in its icy surface, spraying water vapor hundreds of kilometers into space. The spacecraft Cassini flew directly through these plumes. It detected water, organic molecules, hydrogen, several of the ingredients thought necessary for life. These discoveries hint that hidden oceans may be surprisingly common throughout the universe. Many could exist beneath thick blankets of ice, protected from the freezing vacuum above. But some worlds go even further. They possess no parent star at all. Astronomers call them rogue planets. These lonely worlds drift freely through interstellar space after being ejected from their original planetary systems. Gravitational encounters with giant planets or passing stars can slowly destabilize young solar systems. Occasionally, one unfortunate world is flung outward forever. No sunrise, no sunset, only endless darkness stretching across billions of years. At first, such planets appear hopeless. Without a nearby star, temperatures plummet toward the cold of deep space. Surface oceans freeze. Atmospheres may gradually condense. Yet beneath that frozen exterior, another possibility quietly waits. Imagine an Earth-sized rogue planet wrapped beneath an exceptionally thick atmosphere rich in hydrogen. Unlike Earth's relatively thin blanket of air, such an atmosphere could trap geothermal heat with remarkable efficiency. The planet's own internal warmth, though modest, might become enough to maintain liquid water beneath the surface. Above, darkness reigns forever. Below, oceans continue existing in complete silence. No daylight, no blue skies, only warm black seas stretching beneath endless ice. Some scientists have even suggested that life could persist there for billions or perhaps trillions of years. Not because the planet receives energy from a star, but because it never completely loses the heat stored within itself. The universe, once again, proves more imaginative than we expected. Darkness does not always mean death. Indeed, darkness dominates far more of the cosmos than light ever does. Even today, most planets likely wander through vast regions where no nearby sun illuminates the sky. The Milky Way may contain billions of rogue planets. Some estimates suggest they could even outnumber stars themselves, invisible travelers crossing the galaxy in complete solitude. No seasons, no dawn, only the slow passage of cosmic time. If intelligent life ever developed on one of these worlds, its understanding of the universe would be profoundly different from ours. There would be no familiar sun, no constellations shining above. Perhaps only faint, distant stars scattered sparsely across an eternally black sky. Its inhabitants might spend countless generations unaware that planets usually belong to stellar families. To them, drifting alone through darkness would seem perfectly normal. Perspective, as always, depends upon where one begins. The future of the universe makes these lonely worlds even more intriguing. Billions of years from now, star formation will gradually slow. The vast clouds of hydrogen needed to create new stars will become increasingly scarce. Galaxies will grow quieter. Brighter generations of stars will slowly disappear. Eventually, after unimaginable spans of time, nearly every familiar sun will have exhausted its fuel. The great era of starlight will come to an end. Astronomers sometimes call this the degenerate era. It will be an age populated mostly by white dwarfs, neutron stars, black holes, and cooling stellar remnants. Yet even then, not everything immediately freezes into lifeless silence. Some planets may continue orbiting the dim embers of ancient white dwarfs. Others may remain warmed by tidal forces. Still others could wander independently through intergalactic darkness, while their interiors retain precious traces of heat. Life, if it has found enough resilience, may endure astonishingly far beyond the lifetime of ordinary stars. It is a humbling thought. We often associate hope with sunlight, yet nature repeatedly demonstrates that survival can emerge in places where light never reaches. Life does not merely adapt to comfort, it adapts to possibility. Perhaps somewhere in the unimaginable future, beneath kilometers of ancient ice, on a rogue planet drifting between long-dead galaxies, tiny organisms will still be slowly dividing in warm underground oceans. No one will witness their existence. No sunrise will greet them. No sunset will mark the passing of their days. And yet, life may quietly continue. The universe has never promised brightness, only change. Even so, these frozen wanderers remind us of something deeply comforting. The end of one chapter is rarely the end of every story. When stars vanish, planets continue drifting. When galaxies fade, gravity still shapes the darkness. When light disappears, warmth may linger below. The cosmos is astonishingly patient. It wastes almost nothing. Every ending leaves behind the ingredients for another beginning. But eventually, even the oldest surviving worlds will face a challenge unlike any before. Not the death of their suns, not the freezing of their oceans, but the slow fading of time itself as the universe expands farther and farther into an emptiness where even galaxies begin to disappear beyond one another's reach. If you are enjoying this peaceful voyage across cosmic time, subscribe and join us for more stories hidden among the stars. 8. The quiet death of the Milky Way. If you could return to the Milky Way 100 billion years from now, you might be surprised by what you would not see. There would be no great cosmic explosion announcing the end of our galaxy. No single catastrophic event would extinguish its countless stars overnight. Instead, the Milky Way would seem strangely peaceful, almost sleepy. The brilliant blue clusters that now sparkle across its spiral arms would be gone. The glowing clouds where young stars are born would have nearly vanished. The familiar rhythm of stellar birth, the process that has continued for billions of years, would gradually fall silent. Our galaxy would not die in violence. It would simply grow old. Like an ancient forest where no new trees can take root, the Milky Way would slowly become a place filled almost entirely with aging stars. To understand why, we must return to the ingredient that has quietly shaped nearly every chapter of cosmic history: hydrogen. The simplest atom in existence. Just one proton, one electron. Born in staggering quantities during the first few minutes after the Big Bang, hydrogen became the raw material from which almost every visible structure in the universe would eventually emerge. Every shining star is, at its heart, a machine designed to consume hydrogen. Every galaxy is, in many ways, a reservoir storing this precious fuel. For billions of years, giant molecular clouds drifted through the Milky Way like invisible oceans. Cold, dense, immense beyond imagination. Occasionally, gravity would disturb one of these clouds, a slight imbalance, a passing shockwave from a nearby supernova, the gentle pull of another cloud. Slowly, the gas would collapse inward. Temperature increased, pressure mounted. Eventually, a new star ignited. Its first light marked another small victory over darkness. This process has repeated itself for nearly the entire history of our galaxy. The Milky Way currently forms roughly 1 to 3 new stars every year. That may sound modest compared to the hundreds of billions already shining, but over millions of years, those numbers accumulate into magnificent stellar populations. Even tonight, somewhere within our galaxy, invisible clouds are quietly collapsing. Future suns are beginning lives that no human civilization will ever witness from start to finish. Yet every birth comes with a cost. Each newborn star removes hydrogen from the galaxy's supply. Some of that hydrogen will later be returned through stellar winds or gentle stellar deaths, but not all of it. Fusion transforms hydrogen into helium. Later generations of stars create carbon, oxygen, silicon, iron. Elements become locked inside planets, asteroids, moons, and the frozen debris orbiting dying stars. Little by little, the galaxy's original reservoir becomes smaller. Imagine drawing water from an enormous underground lake. At first, the supply appears endless. Year after year, generation after generation, the level barely changes. But eventually, the water begins to fall. Not suddenly, not dramatically, simply a little lower each passing century. The Milky Way's hydrogen follows much the same story. There is still plenty remaining today, enough to continue forming stars for billions more years. But the direction is irreversible. The reservoir is shrinking. Eventually, enormous star-forming clouds become increasingly rare. Without enough cold gas, gravity can no longer assemble fresh stellar nurseries. The machinery that has powered our galaxy for over 13 billion years begins slowing to a crawl. Astronomers sometimes describe galaxies like the Milky Way as quenching. The word sounds gentle, almost peaceful. It means exactly what it suggests: a fire gradually running out of fuel. The flames become smaller, the glowing embers linger. Eventually, almost nothing remains to burn. Long before the final stars die, the Milky Way itself will experience this quiet transition. Its spiral arms, today illuminated by brilliant blue stars only a few million years old, will slowly lose their youthful glow. Those hot blue stars live fast and die young. Without replacements being born, they disappear first. The galaxy's appearance changes. Golden and reddish stars begin to dominate the sky. They are older, cooler, longer-lived. If someone observed our galaxy from afar during this distant future, it would seem softer in color, less energetic, as though the entire Milky Way had entered a long autumn. Ironically, some of its most beautiful features would disappear, precisely because the galaxy had become so calm. The glowing pink nebulae we admire today are stellar nurseries. They shine because newborn stars illuminate surrounding hydrogen clouds. Without new stars, those nebulae gradually fade. The spectacular Orion Nebula, the Eagle Nebula, the Lagoon Nebula, objects that inspire astronomers today represent only temporary chapters in our galaxy's history. One day, they will no longer exist. The sky will become cleaner, simpler, quieter. Even the night itself will slowly change. On Earth, our ancestors looked upward and saw the Milky Way stretching across the heavens like a river of light. That glowing band is created by countless stars packed densely within our galactic disk. Future civilizations, if any still exist, may see a somewhat different sky. Many familiar constellations will have drifted apart. Stars orbit the center of the galaxy at different speeds. Over millions of years, patterns dissolve and reform. Constellations are temporary works of celestial art. Nothing about them is permanent. The Big Dipper, Orion, Scorpius, all will eventually become unrecognizable. The night sky that inspired ancient storytellers is itself slowly evolving. But perhaps the greatest transformation still lies ahead. Several billion years from now, another galaxy approaches. The Andromeda Galaxy has been moving toward us for millions of years. Gravity steadily closes the distance. At first glance, the idea sounds terrifying. Two galaxies colliding. Surely such an event must be unimaginably violent. Yet galaxies are mostly empty space. Although hundreds of billions of stars inhabit each galaxy, the distances between them are so immense that direct stellar collisions remain extraordinarily unlikely. Instead, the galaxies pass through one another like vast clouds of luminous mist. Gravity reshapes their structures. Spiral arms unravel. Stars migrate into new orbits. Gigantic streams of gas stretch across intergalactic space. Eventually, over billions of years, the Milky Way and Andromeda merge into a single enormous elliptical galaxy. Astronomers sometimes nickname this future system Milkomeda. Ironically, this tremendous merger may briefly trigger one final era of star formation. Colliding gas clouds compress, fresh stars ignite. For a little while, the old galaxy enjoys one last burst of youthful energy. It is like autumn leaves, briefly glowing brighter in the evening sun before winter arrives. But even this revival cannot last forever. The available hydrogen continues dwindling. Eventually, the merged galaxy also exhausts its ability to create new generations of stars. Its last stellar nurseries quietly fade. No announcement marks their passing. No universal clock strikes midnight. The final newborn star simply appears. And then, after it, no others follow. From that moment onward, the galaxy enters a fundamentally different age. Its future belongs not to birth, but to memory. Billions upon billions of aging stars continue orbiting in graceful silence. White dwarfs slowly cool. Neutron stars drift invisibly through space. Black holes patiently gather whatever matter still wanders too close. The galaxy itself remains magnificent, but its greatest creative era has ended. There is something unexpectedly comforting in this vision. We often imagine endings as moments, a final heartbeat, a last breath, a closing curtain. The universe prefers something gentler. Entire galaxies grow old almost imperceptibly, not through catastrophe, but through patience, not through destruction, but through gradual change. The Milky Way has never hurried. It took billions of years to build the stars whose light fills our skies tonight. It will take billions more to quietly lay those chapters to rest. And perhaps that is one of the universe's greatest lessons. Even endings, when measured across cosmic time, can be astonishingly peaceful. Yet beyond the fading of galaxies lies an even stranger future. One where the expanding universe stretches so vast that distant galaxies disappear forever beyond each other's horizons, leaving every surviving civilization believing they are utterly alone in an endless sea of darkness. 9. The night when galaxies begin disappearing forever. Imagine standing beneath a perfectly clear night sky. Above you stretches an ocean of stars, much like the one humanity has admired for thousands of years. The familiar glow of your own galaxy still arches across the heavens. But something is missing. No faint smudges of distant galaxies decorate the darkness. No Andromeda, no Triangulum, no clusters of galaxies scattered billions of light years away. Beyond the boundaries of your home galaxy, the universe appears empty. Not because the galaxies have been destroyed, not because their stars have burned out, but because the expanding fabric of space has quietly carried them so far away that their light can never reach you again. It is one of the strangest consequences of living in an expanding universe. Distance is not simply increasing, space itself is growing. When Edwin Hubble first discovered that distant galaxies were moving away from us, the realization transformed our understanding of the cosmos. The universe was not static, it was evolving. Like tiny dots painted upon the surface of an inflating balloon, galaxies were being carried farther apart as space expanded between them. For many decades, astronomers assumed this expansion might gradually slow. After all, gravity should resist the outward motion. Every galaxy attracts every other galaxy. Surely the combined gravity of the universe would eventually reduce the rate of expansion. Instead, observations delivered one of modern astronomy's greatest surprises. The expansion is accelerating. Something mysterious appears to be pushing the universe apart ever faster. Astronomers call this phenomenon dark energy. Despite decades of study, its true nature remains unknown. It neither shines nor absorbs light. It leaves almost no direct trace, yet it dominates the fate of the cosmos. Today, dark energy makes up nearly 70% of the universe's total energy content. Its influence is subtle on the scale of planets, stars, and even galaxies. Gravity still holds those structures together. The Earth will not drift away from the Sun because of dark energy. The Milky Way will not dissolve because of it. But across unimaginably vast distances between clusters of galaxies, it slowly wins. Every billion years, the empty regions separating galaxies become slightly larger. Light traveling through those expanding regions must cross an ever-growing sea of space. At first, the difference is almost impossible to notice. A galaxy a billion light years away becomes a little farther, then a little farther still. Eventually, the distance grows so rapidly that even light, traveling at nearly 300,000 kilometers every second, can no longer make progress. This sounds impossible. How can anything outpace light? The answer lies in a subtle distinction. Nothing is moving through space faster than light. Instead, space itself is expanding. Imagine walking across a moving walkway at an airport. If the walkway moves backward faster than you can walk forward, you never reach the other side. Your speed has not changed. The ground beneath you has. Light faces a similar challenge in the far future. It continues racing across the universe at its usual speed. But the expanding space between galaxies stretches faster and faster. Beyond a certain distance, called the cosmic event horizon, no new light can ever arrive. The galaxies beyond that horizon become permanently unreachable. Their last photons slowly fade into darkness. The night sky grows emptier. This transformation unfolds over astonishing timescales. Billions of years pass before the changes become dramatic. To any civilization living through ordinary lifetimes, the sky seems almost unchanged. But over tens of billions of years, galaxy after galaxy quietly disappears. Not with a flash, not with an explosion, simply by fading until its light can no longer bridge the expanding universe. One by one, the great cities of stars vanish beyond the cosmic horizon. Eventually, only galaxies gravitationally bound to our own remain visible. By then, the Milky Way and Andromeda will already have merged into a single massive galaxy. A handful of nearby dwarf galaxies will continue orbiting this giant system. Together, they form one isolated island, surrounded by an infinite sea that can no longer be explored. Everything beyond that island slips forever out of sight. Future astronomers may face an extraordinary mystery. Imagine an intelligent civilization arising 100 billion years from now. Their telescopes become increasingly sophisticated. They map every visible star, every nebula, every planet within their galaxy. Yet no matter how far they search, they discover nothing beyond. No distant galaxies. No evidence that billions of other galaxies once filled the observable universe. Without those observations, many of the conclusions modern cosmology depends upon would become impossible. There would be no visible expansion of the universe, no Hubble's law, no cosmic web stretching across unimaginable distances. Even the faint afterglow of the Big Bang, the cosmic microwave background, would have stretched into wavelengths so long and so weak that it would become effectively undetectable. The greatest clues to the universe's origin would simply disappear. Those future scientists might conclude that their galaxy constitutes the entire universe, not because they lack intelligence, not because their instruments are inadequate, but because the evidence itself has been carried away by cosmic expansion. In a profound sense, they would become prisoners of time, living too late to witness the universe as it truly once appeared. It is a humbling thought. Humanity exists during a remarkably fortunate era. We live early enough to observe galaxies racing away from one another. We can still detect the ancient radiation left behind by the Big Bang. We can map the large-scale structure of the cosmos. The universe has not hidden its history from us, at least not yet. We are cosmic archaeologists working before the evidence erodes. Every generation of astronomers preserves a little more of a story that future civilizations may never have the opportunity to reconstruct. There is something quietly bittersweet about this realization. When we look through powerful telescopes today, we are not merely seeing distant galaxies. We are witnessing a temporary chapter in cosmic history. The magnificent images captured by modern observatories, vast clusters connected by glowing filaments, spiral galaxies shining across billions of light years, are scenes that no future observer will ever be able to reproduce. The universe itself is slowly closing the curtain. And yet, even as distant galaxies disappear, the local universe remains astonishingly rich. Stars continue orbiting, planets continue circling their suns, black holes quietly shape their surroundings. Within one gravitationally bound galaxy, billions of stories still unfold. Life, should it continue to exist, may never feel lonely. It is only when we step back to consider the entire cosmos that the true scale of the loss becomes apparent. The observable universe slowly shrinks, not because it becomes smaller, but because less of it remains observable. Knowledge itself becomes more difficult. History becomes harder to recover. The cosmos grows quieter. Perhaps this is one of the universe's most profound lessons. Observation depends upon timing. To understand reality, it is not enough simply to exist. One must also exist at the right moment. We are fortunate enough to live during an age when the universe still reveals much of its past. Future civilizations may inherit a cosmos every bit as magnificent, yet far less willing to explain where it came from. Still, even the disappearance of galaxies is not the final chapter. Long after the last distant lights have slipped beyond the cosmic horizon, the stars within our own galaxy will continue aging one by one. White dwarfs will cool into darkness. Neutron stars will drift silently through space. Black holes will become the longest-lived monuments to an era when the universe was filled with brilliant suns. And beyond them lies a future so unimaginably distant that even time itself begins to lose the meaning we give it today. 10. The era when only black holes remain. Take a slow breath and let your imagination drift farther than any telescope has ever seen. Picture the night sky, not the one above your home, filled with familiar constellations. Not even the ancient sky our earliest ancestors admired thousands of years ago. Instead, imagine a sky that contains nothing. No shimmering Milky Way stretching overhead. No neighboring galaxies glowing faintly across unimaginable distances. No brilliant stars tracing patterns that inspire myths and navigation, only endless darkness. This is not because the universe has disappeared. It is because almost every source of light has finally gone out. By this unimaginable chapter of cosmic history, the universe has already survived through trillions upon trillions of years. Star formation ended long ago. The last generations of red dwarfs exhausted the tiny reserves of hydrogen that once allowed them to shine. White dwarfs cooled into frozen black dwarfs. Neutron stars slowly lost their remaining heat. Galaxies themselves became quiet museums of ancient stellar corpses. Yet one type of object continued to endure: black holes. Ironically, the only things that never emitted light would become the final dominant structures in the observable universe. It almost feels poetic. Throughout cosmic history, black holes were often portrayed as monsters, devouring stars, swallowing gas clouds, and hiding everything behind invisible horizons. But by the time every star has faded, they become the last surviving monuments to everything that once existed. They are the universe's memory. Each black hole carries inside it the remains of countless ancient suns. Some contain the ashes of individual massive stars. Others, known as supermassive black holes, contain millions or even billions of solar masses, gathered during countless galactic mergers. The brilliant galaxies that once sparkled across space have all collapsed into quiet gravitational relics. At the center of almost every former galaxy sits one enormous black hole, silent, patient, waiting. Surprisingly, this era is not completely motionless. Gravity never truly stops working. Although galaxies no longer produce new stars, the remnants inside them continue their slow gravitational dance. Black dwarfs occasionally pass close enough to disturb one another. Dead stellar remnants exchange energy over incomprehensible spans of time. Some are flung into intergalactic space forever. Others spiral inward. Eventually, many of these ancient remnants fall toward the central black hole. No spectacular fireworks accompany these final journeys. Unlike young galaxies rich with gas, there is almost nothing left to create bright accretion disks. A lonely black dwarf drifts inward. A cold neutron star slowly crosses the event horizon. A frozen planet disappears without a sound. Each tiny addition makes the black hole slightly larger, slightly heavier, slightly more isolated. This process continues for unimaginable lengths of time. In fact, gravitational interactions inside old galaxies become increasingly chaotic. Given enough time, almost every remaining object is eventually either ejected into empty space or swallowed by the central black hole. The galaxies themselves slowly dissolve. Not through explosions, not through collisions, simply through patience. Gravity acts slowly, but it rarely forgets. As trillions become quadrillions, quadrillions become quintillions, the universe grows emptier still. Distance itself becomes another form of silence. Cosmic expansion continues stretching space faster and faster. The surviving black holes become separated by distances so enormous that even light, if there were any left to emit, could never bridge them. Each black hole effectively inhabits its own isolated universe. Imagine floating near one. There would be almost nothing visible. No nearby stars, no glowing nebulae, no colorful galaxies decorating the darkness. Only an invisible gravitational well surrounded by perfect blackness. If not for the bending of distant background radiation, what little remains, you might never know the black hole exists at all. Ironically, this may represent one of the simplest universes that has ever existed. During our present era, complexity surrounds us everywhere. Stars create heavy elements. Planets support chemistry. Galaxies collide. Life evolves. Civilizations ask questions. But complexity requires energy, and usable energy slowly disappears. Physicists describe this through the concept of entropy. As entropy increases, differences become smaller. Hot objects cool, bright objects fade. Ordered structures dissolve. The universe slowly approaches thermal equilibrium. Black holes seem almost immune to this trend. They continue gathering mass long after every other cosmic engine has stopped. For a while, they become the final islands of structure in an increasingly featureless sea. Yet even black holes cannot escape time forever. This realization shocked physicists during the 20th century. For decades, black holes were believed to be perfectly eternal. Nothing escaped them. Nothing changed them. Nothing could destroy them. Then Stephen Hawking made one of the most astonishing discoveries in theoretical physics. Quantum mechanics suggested that black holes are not completely black after all. Tiny quantum fluctuations near the event horizon allow an incredibly faint form of radiation to emerge. This phenomenon became known as Hawking radiation. The effect is unimaginably weak for large black holes. A stellar black hole would take around 10 to the power of 67 years to evaporate. Supermassive black holes survive vastly longer, up to roughly 10 to the power of 100 years or more. Numbers like these are almost impossible to comprehend. If every second since the Big Bang were represented by one grain of sand, the pile would still be insignificant compared to these timescales. Black holes appear immortal only because human minds evolved to experience moments measured in heartbeats rather than googles of years. Eventually, however, even immortality runs out. Very slowly, each black hole radiates away tiny amounts of mass. The largest ones lose energy at an almost absurdly slow rate. For billions upon billions of years, nothing noticeable happens. Then trillions, then quadrillions, then numbers so large that language itself begins to lose meaning. The black hole shrinks almost imperceptibly. Its temperature rises. The evaporation accelerates. Still, there is no audience left to witness this astonishing transformation. No civilizations, no planets, no stars. Only darkness observing darkness. It is a strangely beautiful thought. The greatest gravitational giants in existence spend nearly all of cosmic history growing larger, only to spend an even longer eternity quietly disappearing. Without explosions, without applause, without farewell. Perhaps that is the deepest lesson hidden inside black holes. Even the most powerful structures nature can build are temporary. Nothing remains untouched by time. Not mountains, not galaxies, not stars, not even the objects that once seemed capable of swallowing eternity itself. The universe has always favored change over permanence. Everything flows. Everything evolves. Everything eventually transforms into something quieter than before. Yet there is something comforting about this realization. The atoms inside your body were forged inside stars that lived billions of years ago. Those stars died so planets could form. Planets formed so chemistry could become biology. Biology evolved into consciousness. And consciousness now contemplates the future of black holes that will outlive every civilization by inconceivable stretches of time. For one brief moment in the middle of cosmic history, the universe became aware enough to ask where it is going. That moment is us. And while black holes may inherit the universe after every star has faded, their reign too is only another chapter. Because beyond the age of black holes lies an even stranger destination. A future where almost nothing remains except faint particles, expanding space, and time itself continuing into an unimaginable silence. 11. The slowest explosion in cosmic history. When we imagine an explosion, we think of violence compressed into an instant. A flash of blinding light, a deafening shockwave, and destruction spreading outward in moments. Supernovae, the spectacular deaths of massive stars, seem to fit that image perfectly. Even on a cosmic scale, they erupt in what feels like the blink of an eye. But the universe has a very different definition of time. There exists another kind of explosion, one so unimaginably slow that no civilization could ever witness it from beginning to end. It unfolds not over seconds, years, or even billions of years, but across stretches of time that dwarf the entire history of the cosmos itself. It is an explosion without urgency, a transformation so patient that the universe itself barely notices it happening. To understand this extraordinary finale, we must travel far beyond the era of stars, beyond galaxies glowing in the darkness, beyond even the reign of black holes. We arrive in an age where almost nothing changes from 1 trillion years to the next. By now, nearly every familiar object has disappeared. The brilliant galaxies that once painted the heavens have faded into darkness. The glowing nebulae that once birthed stars are gone. The great stellar civilizations that might have flourished around warm suns have become unimaginably ancient memories. Only black holes remain as the dominant structures of the universe. For a long time, they appear eternal. Their gravity is so overwhelming that even light cannot escape. Entire stars once vanished into their depths, adding to their mass and making them even larger. Supermassive black holes containing billions of solar masses rested quietly at the centers of ancient galaxies, while smaller stellar black holes drifted through empty space. For countless ages, nothing seems capable of changing them. If anything deserves the word permanent, surely it would be a black hole. Yet nature rarely grants true permanence. In the 1970s, physicist Stephen Hawking revealed something astonishing. According to quantum mechanics, black holes are not completely black after all. They slowly radiate tiny amounts of energy. This phenomenon, now called Hawking radiation, emerges from the strange behavior of quantum fields near the event horizon. Empty space is never truly empty. Tiny fluctuations constantly create pairs of virtual particles that normally annihilate one another almost immediately. Near the edge of a black hole, however, something remarkable can happen. One particle falls inward, the other escapes. To a distant observer, it appears as though the black hole itself has emitted a particle. With every escaped particle, the black hole loses an almost unimaginably tiny amount of mass. Not enough to notice, not enough to matter. At least, not at first. Imagine removing a single grain of sand from Mount Everest every million years. No observer could detect the mountain shrinking. Generation after generation would conclude it was unchanged. Yet if the process continued long enough, eventually even Everest would disappear. A black hole follows the same quiet logic. Every particle emitted carries away a little energy. Every little loss makes the black hole slightly smaller. As it shrinks, something unexpected occurs. Its temperature rises. Large black holes are astonishingly cold. A supermassive black hole at the center of a galaxy is colder than the cosmic microwave background that currently fills space. Today, it actually absorbs more energy than it emits. But in the unimaginably distant future, as the universe continues expanding and cooling, even this balance changes. Eventually, the surrounding universe becomes colder than the black hole itself. Only then does evaporation truly begin. The process remains agonizingly slow. A stellar mass black hole would require roughly 10 to the power of 67 years to disappear. That number is almost impossible to grasp. The current age of the universe is only about 13.8 billion years, approximately 10 to the power of 10 years. A black hole survives for a period 57 orders of magnitude longer. Even that is merely the beginning. The largest black holes, containing billions of solar masses, may endure for around 10 to the power of 100 years. This number is so enormous that ordinary language fails. If every atom in the observable universe somehow represented another universe as old as ours, and each of those universes contained another equally vast collection of atoms, we would still fall hopelessly short of imagining such a timescale. Time itself begins to lose meaning. Civilizations cannot be measured against it. Stars cannot be measured against it. Even galaxies become fleeting sparks by comparison. Throughout these unimaginable eons, Hawking radiation continues without pause. No dramatic fireworks, no thunderous blast, only a steady whisper of escaping particles, photon by photon, neutrino by neutrino. Tiny fragments of energy drift into an almost perfectly empty universe. Eventually, the black hole becomes noticeably smaller. As its mass decreases, evaporation accelerates. What once seemed frozen begins changing more quickly. Still, quickly remains a relative term. Millions upon millions of years pass between meaningful differences. Then billions. Then trillions. Finally, after ages beyond comprehension, the end approaches. The black hole has become tiny. Its temperature has risen enormously. Now the radiation pours out at an increasing rate. The once silent giant suddenly releases energy far more rapidly than before. Its final moments resemble the closest thing this patient process has to an explosion. Yet even this ending is modest compared to the supernovae that once illuminated young galaxies. There is no enormous shockwave tearing through neighboring stars. There are no planets waiting nearby to witness the flash. The surrounding universe has become almost completely empty. The final burst simply releases the remaining energy stored within the black hole's mass. Then, nothing. The event horizon vanishes. The singularity, whatever its true nature may be, ceases to exist. The greatest gravitational prison ever created quietly dissolves into radiation. One of the universe's oldest survivors is gone forever. Multiply this story by every black hole that has ever existed, one by one, over incomprehensible stretches of time. The stellar black holes disappear, the intermediate ones follow. At last, even the supermassive giants at the centers of ancient galaxies evaporate. The universe slowly loses its final engines of structure. No stars remain, no galaxies actively evolve. No black holes anchor gravity's deepest wells. Only thin streams of low-energy particles drift through an ever-expanding sea of darkness. Some physicists describe this future as the heat death of the universe. Not because everything becomes hot. Quite the opposite. Energy spreads so evenly that no meaningful work can occur. No temperature differences remain to power engines. No dense clouds collapse into stars. No chemical gradients drive complexity. Everything approaches equilibrium. The universe does not end with violence. It ends with stillness. It becomes increasingly difficult to define the passage of time itself. Without changing objects, clocks lose meaning. Without stars rising and setting, days no longer exist. Without galaxies moving through the sky, there are no seasons of the cosmos. Time continues mathematically, yet almost nothing remains to experience it. Perhaps this is the slowest explosion in cosmic history. Not a single event, not a sudden catastrophe, but the patient evaporation of every black hole across spans of time so vast they transform our understanding of permanence itself. The universe teaches the same lesson again and again. Nothing lasts forever. Stars bloom and fade. Galaxies collide and grow quiet. Black holes, once believed immortal, eventually dissolve. Even darkness changes. Even emptiness evolves. And somehow there is a quiet beauty in that realization. The cosmos has never relied on permanence to create wonder. Instead, its beauty has always come from transformation. Every ending becomes the beginning of something else. Every structure, no matter how immense, eventually yields to time. Even the slowest explosion imaginable is simply another chapter in the universe's endless story. A story written not in moments, but across eternities so vast that silence itself becomes the final narrator. 12. The black holes that eventually evaporate. After surviving every star, after outliving every galaxy, after patiently watching the universe grow colder for longer than numbers can comfortably describe, even black holes must finally face something they have defeated for almost all of cosmic history: the passage of time. For billions of years after Stephen Hawking first proposed that black holes could slowly evaporate, the idea seemed almost impossible to believe. How could an object famous for trapping light somehow lose energy? How could something that allows nothing to escape quietly disappear? The answer lies in one of nature's strangest truths. Reality is never as empty as it appears. If we could somehow zoom down to the smallest scales imaginable, not to atoms, nor even to the particles inside atoms, but to the restless quantum fabric beneath everything, we would discover that empty space is constantly alive. Tiny fluctuations ripple everywhere. Particles briefly appear. Their opposites appear beside them. Almost instantly, they annihilate one another, leaving space looking empty once again. This endless microscopic dance happens everywhere throughout the universe, even in the deepest vacuum, even inside the vast darkness between galaxies, even beside the event horizon of a black hole. Normally, these virtual particles disappear so quickly that the universe never notices. But a black hole changes the rules. Near the edge of its event horizon, gravity is so intense that occasionally one particle falls inward before it can reunite with its partner. The second particle escapes. To distant observers, it looks as though the black hole itself emitted that particle. No object inside the event horizon actually climbs back out. Instead, the black hole quietly pays the energy required for the escaped particle by sacrificing an almost unimaginably tiny portion of its own mass. One particle, then another, then another. If you could somehow stand outside a supermassive black hole with perfect instruments, you would never witness a dramatic transformation. You would wait and wait, perhaps for millions of years, before measuring even the slightest difference. The black hole would seem completely unchanged. Yet nature is patient. It has never been concerned with human attention spans. Every escaped particle is like one drop of water evaporating from an immense ocean. No single drop matters, but enough drops given enough time can empty even the largest sea. Black holes evaporate in exactly this way, not through violence, not through collapse, but through an endless whisper of disappearing mass. This may be the slowest process the universe has ever invented. Imagine holding an hourglass. Instead of grains of sand falling every second, only one grain falls every trillion years. Now imagine the hourglass contains more grains than there are atoms in every galaxy we can observe. That image still understates the patience required. A black hole born from the collapse of a massive star might survive for around 10 to the 67th years. The supermassive giants that once ruled galactic centers endure even longer. Some calculations suggest they may persist for around 10 to the 100th years before completely evaporating. By comparison, our universe today is only about 13.8 billion years old. Human civilization occupies less than the final fraction of a second if the entire history of one supermassive black hole were compressed into a single calendar year. Everything humanity has ever accomplished, every language, every empire, every work of music, every scientific discovery, every memory, would vanish almost instantly on that cosmic calendar. The black hole would barely notice our existence. And yet, eventually even it begins to shrink. Interestingly, the smaller a black hole becomes, the hotter it grows. This seems completely backwards compared to everyday experience. A campfire cools as it burns out. A cup of coffee cools as it loses heat. But black holes obey different mathematics. As they lose mass, their temperature rises. That higher temperature allows them to emit radiation more quickly. The evaporation slowly accelerates. For most of their unimaginably long lives, black holes change almost not at all. Then, near the very end, their quiet fading becomes noticeably faster. It is almost as if the universe saves all the visible change for the final pages of the story. Imagine watching a gigantic iceberg floating in an endless frozen ocean. For centuries, it appears motionless. Only careful measurements reveal it has become slightly smaller. Then, after ages beyond counting, its melting suddenly becomes obvious. Cracks spread, edges soften. The remaining ice disappears rapidly into the surrounding sea. A black hole experiences something surprisingly similar, except instead of melting into water, it dissolves into pure radiation. There is something profoundly beautiful about this ending. For nearly all of cosmic history, black holes represented ultimate permanence. Entire stars vanished inside them. Galaxies revolved around them. Even light surrendered to them. They seemed to stand outside the ordinary cycle of birth and death. But Hawking radiation restores them to the same universal story shared by everything else. Nothing escapes change. Not stars, not planets, not galaxies, not black holes. Perhaps permanence was never part of the universe's design. Perhaps transformation has always been the deeper law. As each black hole evaporates, the energy locked inside it returns to the wider universe. In a sense, nothing is truly destroyed. Matter became gravity. Gravity became mass. Mass became radiation. The universe continuously rewrites its own contents without ever needing to invent new ingredients. This quiet recycling has been happening since the first seconds after the Big Bang. It simply unfolds on ever larger timescales. One fascinating question remains unanswered. What happens to the information that once fell into a black hole? Every star it consumed, every planet, every photon, every atom, even hypothetical civilizations that might have crossed its event horizon. Does all of that information disappear forever? Or does quantum mechanics somehow preserve it in ways we do not yet understand? This mystery became known as the black hole information paradox. It has challenged physicists for nearly half a century. Some theories suggest the information is encoded within Hawking radiation itself. Others propose that the event horizon behaves like an unimaginably complex holographic surface. Still others argue that our understanding of space and time remains incomplete. As of today, no consensus exists. Perhaps future physics will uncover the answer, or perhaps the final secret of black holes will remain hidden until a deeper theory unites gravity with quantum mechanics. There is something wonderfully humbling about that uncertainty. The universe has allowed us to calculate the lives of stars billions of years into the future. It has allowed us to predict the deaths of galaxies and the evaporation of black holes, yet it still guards some of its greatest mysteries. Even at the end of time, there are questions left unanswered. As the last supermassive black hole finally completes its evaporation, no audience remains to celebrate. No astronomers record the event. No civilizations watch from distant planets. No galaxies illuminate the background. Only an immeasurably dark universe receives the final pulse of radiation. For a brief instant, one of the oldest objects in existence releases the last of its stored energy. Then the darkness becomes just a little deeper, a little quieter, a little emptier. The era of black holes is over. The universe enters a chapter unlike any before it. No brilliant structures dominate the cosmos anymore. No gravitational giants shape the destiny of surrounding matter. Only faint particles drift farther apart as space itself continues expanding without end. It is difficult to call this an ending. It feels more like a final exhale. The universe, after creating galaxies, stars, planets, oceans, mountains, forests, and perhaps countless civilizations, slowly relaxes into silence. And perhaps that silence is not something to fear, because for one extraordinary moment, somewhere near the beginning of all these unimaginable ages, the universe produced beings capable of wondering how the story would end. That curiosity is its own kind of light, a light that burned briefly beneath ordinary stars, yet managed to illuminate the fate of black holes themselves. If tonight's journey is bringing a little peace to your evening, subscribe so we can continue discovering what lies beyond the end of time. There are still a few more astonishing chapters waiting beyond the fading of the last black hole, where even space, time, and the very fabric of reality may hold one final surprise. 13. The last atoms waiting in silence. For almost everything we have witnessed throughout this journey, there has always been something left behind. When the first stars died, they left heavier elements. When galaxies collided, they created larger galaxies. When stars exhausted their fuel, white dwarfs, neutron stars, and black holes remained as quiet monuments to lives once brilliantly lived. Even after the last ordinary stars disappeared, black holes continued lingering across the darkness for incomprehensibly long ages. The universe always seemed reluctant to erase its own history. But eventually, an unsettling possibility begins to emerge. What if even matter itself cannot last forever? Imagine drifting through a universe so old that every recognizable structure has vanished. No glowing galaxies decorate the sky. No stars remain to cast light across space. Black holes have already evaporated into faint whispers of radiation. Even the cold remnants of planets have long since been torn apart. Only isolated particles remain. Tiny survivors scattered across an ever-expanding cosmos. They drift farther apart every second, surrounded by distances so vast that even light would require unimaginable spans of time to cross them. For these lonely particles, neighbor no longer has meaning. Each one exists almost completely alone. This possible era is sometimes called the degenerate era, or even more poetically, the era of the last matter. It stretches so far into the future that numbers become almost meaningless. Not billions, not trillions, not even numbers with thousands of digits can comfortably describe these timescales. Human language evolved to describe forests, rivers, mountains, and seasons. It was never designed to describe futures extending beyond 10 to the power of 40, 10 to the power of 100, or perhaps even 10 to the power of 1,000 years. Yet modern physics quietly attempts exactly that. One of the greatest mysteries concerns something that seems perfectly permanent today: the proton. Every atom around you contains protons. The atoms inside your body, the atoms in your chair, the oxygen floating through the room, the silicon inside computers, the iron deep within Earth's core. Everything familiar depends on the remarkable stability of these tiny particles. For generations, scientists assumed protons lived forever. After all, no experiment has ever observed one decaying. But some theories that attempt to unite the fundamental forces of nature suggest an astonishing possibility. Protons may not actually be eternal. They may simply live so incredibly long that no human civilization has existed long enough to witness even a single confirmed decay. Current experiments indicate that if proton decay exists, its average lifetime must exceed roughly 10 to the power of 34 years. To appreciate how extraordinary that number is, remember that our universe today is only about 13.8 billion years old. That is approximately 1.38 times 10 to the 10th power years. The lower limit for proton lifetime exceeds the universe's current age by more than 24 orders of magnitude. It is as though a mayfly attempted to determine whether mountains eventually erode, not over centuries, but over spans longer than entire geological epochs. Our perspective is simply too brief. If proton decay is real, then every object composed of ordinary matter carries an invisible clock. Not a clock measuring seconds, not even one measuring billions of years. A clock whose ticking is almost unimaginably slow. Each proton waits. Most wait without change. Some may eventually transform into lighter particles, releasing tiny bursts of energy before disappearing forever. One by one, quietly, without violence, without spectacle, there is no great explosion marking the end of matter. No cosmic catastrophe. Just an endless sequence of incredibly rare events occurring across an ever dimmer universe. A mountain would not crumble all at once. Instead, every grain of sand would quietly vanish individually over periods vastly exceeding the age of everything we know. Eventually, planets would lose their solidity. Asteroids would dissolve. White dwarfs would slowly disintegrate. The remaining debris of ancient galaxies would simply fade into clouds of lightweight particles. Even the atoms that once formed living creatures would no longer exist. Every heartbeat ever experienced, every smile, every civilization, every library, every ocean, every memory stored inside physical matter would finally surrender to time. The universe would become increasingly transparent, increasingly empty, increasingly quiet. Yet not all physicists agree that this fate is inevitable. The truth is that proton decay has never been observed. Despite decades of searching in vast underground detectors filled with thousands of tons of ultra-pure water or other sensitive materials, not a single unambiguous proton decay event has been confirmed. This absence is itself fascinating. Nature may simply preserve protons forever. If so, matter could survive almost indefinitely, even after stars and black holes have disappeared. In that version of the future, lonely electrons, protons, and atomic nuclei continue drifting through infinite darkness. Cold, silent, nearly motionless. Occasionally, gravity might bring two particles together over absurdly long timescales. A rare collision, a brief interaction, then separation once more. The universe would resemble a vast ocean whose waves have almost completely frozen. Motion still exists, but it unfolds so slowly that change becomes nearly impossible to notice. There is another strange possibility. Quantum mechanics teaches us that particles are never perfectly still. Even at absolute zero, tiny fluctuations persist. Reality itself possesses an irreducible uncertainty. These microscopic uncertainties never entirely disappear. Over sufficiently long periods, they continue producing subtle events that ripple through otherwise empty space. Vacuum fluctuations flicker in and out of existence. Virtual particles briefly appear before vanishing again. The universe never becomes perfectly static. Instead, it rests in an almost dreamlike state of minimal activity. If an observer somehow survived into these impossible ages, they might wait longer between significant events than all previous cosmic history combined. Imagine witnessing one particle interaction, then waiting another trillion universes worth of time before observing the next. Patience itself would lose meaning. Time would no longer feel like a flowing river. It would resemble isolated droplets falling across an infinite desert. Some cosmologists wonder whether information can truly disappear during these ages. Physics increasingly suggests that information may be fundamentally conserved, even if transformed beyond recognition. If that is true, then somewhere within the unimaginably diluted fabric of the far future, faint echoes of everything that has ever happened still remain encoded in subtle correlations. Not memories in any human sense, not stories, not photographs, but mathematical traces embedded within reality itself. The birth of the first stars, the formation of Earth, the rise of life, every conversation, every sunrise, every heartbeat. Perhaps none are truly erased, only scattered beyond any hope of reconstruction. It is a strangely comforting thought. The universe may never completely forget, even when no one remains to remember. Yet there is an even deeper question waiting beneath all of this. Why does matter exist at all? Shortly after the Big Bang, matter and antimatter should have been created in nearly equal amounts. Had perfect symmetry prevailed, every particle would have met its opposite. Everything would have annihilated into pure radiation. No atoms, no stars, no planets. No people asking questions beneath the night sky. Some tiny imbalance, perhaps only one extra particle of matter for every billion matter-antimatter pairs, changed everything. That almost imperceptible asymmetry became every galaxy we have ever observed. Every living cell, every human civilization, every atom reading these words. The future of matter, therefore, is also the future of that ancient imbalance. Whether protons eventually decay or survive forever, the existence of ordinary matter itself remains one of the greatest miracles hidden within modern cosmology. Its survival has already lasted 13.8 billion years. Its future may extend incomprehensibly farther, or it may slowly dissolve into lighter particles until nothing recognizable remains. We simply do not yet know. Science is wonderfully honest about uncertainty. Sometimes the greatest discovery is recognizing where certainty ends. As we continue drifting through this unimaginable future, the universe grows quieter than any silence we can truly imagine. Galaxies have disappeared, stars are gone, black holes have evaporated. Only scattered remnants of matter remain, waiting through intervals so immense that even eternity seems too hurried a word. And somewhere within that endless darkness, the final atoms continue their patient vigil, perhaps immortal, perhaps slowly fading, holding the last fragile threads connecting the distant future to the brilliant cosmic dawn from which everything began. Their silence is not empty. It is the longest echo of creation itself. 14. The universe after everything has ended. For billions upon billions of years, the universe has always had something left to show. There were galaxies glowing like islands across an endless sea. There were stars forging the elements that would someday become oceans, mountains, forests, and living mines. There were planets circling patiently beneath gentle sunlight. Later came quieter ages. The stars slowly disappeared. Galaxies grew dark. Black holes became the final giants still shaping the silent cosmos. Even they, as we discovered, were never truly eternal. One by one, through the unimaginably slow process of Hawking radiation, they evaporated into faint streams of particles until nothing recognizable remained. And so we arrive at perhaps the strangest chapter of all, a universe after everything has ended. Not after humanity, not after Earth, not after the Milky Way, but after nearly every structure the cosmos has ever built has finally disappeared. At first, it sounds impossible to imagine. Our minds naturally picture space as filled with stars. Even the darkest night sky still contains thousands of distant lights. Yet the true future may be something entirely different. Imagine looking in every direction and finding absolute darkness. No constellations, no galaxies stretching across the heavens, no glowing nebulae, no distant suns waiting beyond the horizon. The universe has not become smaller, it has become emptier. Expansion has continued for such extraordinary lengths of time that the remaining particles are separated by distances beyond comprehension. Even light itself struggles to connect one lonely particle with another. Space has become almost perfectly transparent, almost perfectly silent. If an observer somehow existed during this era, they might wait longer than today's age of the universe before witnessing even a single meaningful interaction between particles. Time itself begins to lose its familiar rhythm. Nothing rises, nothing sets, nothing grows older in any recognizable way. The universe enters a kind of endless stillness. Yet physics tells us that absolute nothingness is surprisingly difficult to achieve. According to quantum theory, even the emptiest vacuum is not truly empty. Instead, empty space possesses tiny fluctuations that continuously ripple beneath reality. Virtual particles briefly appear, then vanish again. These events occur on scales so incredibly small that they never produce stars or planets. But they remind us that existence itself is never perfectly motionless. Reality continues whispering, even after its loudest voices have gone silent. Some physicists describe this as the quantum vacuum. Rather than an empty stage after the actors have left, it resembles an ocean whose surface appears perfectly calm, while microscopic waves continue dancing below. Nothing dramatic happens, yet nothing is completely still. There is another remarkable possibility. Even after every familiar object has disappeared, the universe continues expanding. Galaxies no longer drift apart because there are no galaxies left. Instead, space itself quietly grows larger. Every second creates more emptiness than existed before. The darkness becomes deeper, not because darkness changes, but because there is simply more room for it. If dark energy continues behaving as it does today, this expansion may never stop. The universe will not collapse back into a fiery ending. Instead, it stretches forever. Distances become infinite. Isolation becomes complete. Every surviving particle becomes an island floating inside an ocean with no shores. It is difficult for human intuition to grasp numbers this large. Suppose one particle sends out a photon. There may be no other particle close enough to receive it before expansion carries everything even farther apart. Messages lose their destinations. Light loses its audience. The universe still exists, but communication has nearly ended. And yet, perhaps the most fascinating question remains unanswered. Does time itself still have meaning? We usually measure time through change. A clock ticks, the earth rotates, atoms vibrate, people grow older. These familiar cycles give time its texture. But in a universe where almost nothing changes, what distinguishes 1 trillion years from another? The equations of physics continue keeping track, yet experience would become almost impossible. Without events, time begins feeling less like a flowing river and more like an endless, featureless landscape extending beyond every horizon. Some philosophers have wondered whether time requires observers. Physics suggests otherwise. The universe does not need someone watching in order for time to continue. But without change, time becomes strangely invisible. It passes quietly, unnoticed by anything capable of measuring it. There is another possibility that has fascinated cosmologists for decades. Could this seemingly empty universe eventually give birth to something entirely new? Quantum mechanics occasionally allows extraordinarily rare fluctuations. Given enough time, far more time than any previous era of cosmic history, tiny random events become mathematically inevitable. Most are insignificant. A particle appears. A particle disappears. But over unimaginable stretches of eternity, some physicists have asked whether larger fluctuations might occasionally occur. Could an entire new region of space emerge? Could another Big Bang somehow begin within the quantum vacuum? This idea remains deeply speculative. No one knows whether our universe possesses the conditions necessary for such rebirth. Some cosmological models suggest it might. Others argue it cannot happen. Science has not yet settled the question, but the possibility itself is breathtaking. Perhaps endings are never completely final. Perhaps what appears to us as the ultimate silence is simply another beginning, waiting on timescales beyond imagination. Even if no new universe is born, the vacuum itself may continue existing indefinitely. An endless sea of expanding space, tiny quantum fluctuations. No stars, no planets, no black holes. Only the mathematical fabric of reality quietly persisting. It is remarkable to realize how much of existence depends on imbalance. The early universe contained slightly more matter than antimatter. That tiny difference allowed galaxies to form. Gravity amplified tiny variations in density until stars ignited. Inside those stars, nuclear fusion built the atoms that would eventually become life. Every familiar structure arose because perfect symmetry was broken ever so slightly. When those structures finally disappear, symmetry gradually returns. The universe becomes smoother, more uniform, less capable of building complexity. Entropy, the great organizer of disorder, has nearly completed its work. Energy still exists, but it has become spread so evenly that almost nothing useful can happen with it. There are no great engines left to power change. No hot stars shining beside cold planets. No temperature differences waiting to be exploited. Everything drifts toward equilibrium. This is sometimes called the heat death of the universe. Despite its dramatic name, it is not an explosion. It is not destruction. It is simply the slow fading of every opportunity for organized activity. The universe does not die in a scream. It falls asleep, very, very slowly. There is something unexpectedly peaceful about this picture. The cosmos began in extraordinary brightness. Temperatures beyond imagination. Matter racing outward at incredible speeds. Violent collisions. Blazing stars. Exploding galaxies. Black holes consuming entire solar systems. Over trillions upon trillions of years, all that turbulence gradually softens. The universe ages with remarkable grace, like an ocean after a storm finally settling beneath a calm sky. Silence replaces fire. Stillness replaces motion. Darkness replaces light. Yet none of this diminishes the wonder of our own moment. Quite the opposite. We live during one of the rare eras when galaxies still fill the heavens. Stars continue being born. Planets remain warm enough for oceans. Chemistry still creates life. Conscious minds can gaze upward and ask questions about beginnings and endings. We exist during the universe's golden afternoon, long before its final night arrives. Perhaps that is the greatest lesson carried across this immense journey. Impermanence does not make existence less meaningful. It makes it astonishing. Every sunrise on Earth is possible only because countless generations of stars lived and died before our sun was born. Every breath contains atoms forged inside ancient stellar furnaces. Every heartbeat is connected to events stretching back nearly 14 billion years. And someday, unimaginably far in the future, even those atoms may finally surrender to time. Until then, the universe continues telling its extraordinary story, not through endless permanence, but through transformation, from light into darkness, from simplicity into complexity, from chaos into order, and eventually from motion into profound stillness. When every star has faded, when every planet has crumbled, when every black hole has evaporated, when even the last atoms have fallen silent, the universe may not end with a final event that anyone could witness. Instead, it simply continues, quiet, infinite, patient, holding within its endless emptiness the memory of every galaxy that ever shimmered, every world that ever turned beneath the sun, and every curious mind that once looked into the night sky and wondered how the story would end. Perhaps in that sense, the universe never truly loses its history. It merely carries it forward into an eternal silence deeper than words could ever describe. 15. The question time may never answer. After traveling farther into the future than any civilization could ever hope to survive, we finally arrive at a place where even imagination begins to lose its footing. The stars are gone. The galaxies have faded beyond recognition. Black holes, once thought to be immortal, have quietly evaporated into faint whispers of radiation. Perhaps even the last atoms have surrendered to time. The universe has become almost perfectly empty, almost perfectly still. And yet, one question continues lingering in the silence. Is this truly the end, or is the end simply another beginning waiting beyond our understanding? It is a question no telescope can answer, no spacecraft can travel far enough to investigate. No experiment on Earth can recreate the unimaginable conditions of the universe trillions upon trillions of years from now. Instead, physicists are left with mathematics, equations, theories, and the remarkable realization that some of those equations leave the door ever so slightly open, not to certainty, but to possibility. Throughout this journey, we have watched the universe transform itself again and again, from a hot sea of particles into glowing stars, from stars into galaxies, from galaxies into darkness. Every age seemed permanent to whatever existed within it. Yet every age eventually gave way to another. Perhaps that pattern itself invites one final question. Why should change stop now? One of the most fascinating ideas in modern cosmology begins with something surprisingly familiar. Imagine flipping a coin. Most of the time it lands randomly on heads or tails. But if you continue flipping forever, millions, billions, trillions of times, extraordinary sequences eventually become inevitable. 10 heads in a row, 100, 1,000. Given unlimited opportunities, events that seem impossible gradually become unavoidable. Physics sometimes behaves in much the same way. The quantum world is filled with tiny fluctuations. Even empty space is never perfectly empty. Invisible fields gently fluctuate. Particles briefly appear before disappearing again. Reality itself possesses a subtle restlessness that never entirely fades. Today, these fluctuations are unimaginably small. They cannot suddenly create galaxies out of nothing. They cannot rebuild the observable universe before our eyes. But over timescales vastly exceeding anything we can comprehend, some theoretical physicists have wondered whether incredibly rare fluctuations might eventually produce something much larger, not merely particles, perhaps entire regions of space. This idea remains highly speculative. No experiment has confirmed it. No observation has ever witnessed such an event. Yet mathematics does not immediately forbid every version of it. Some cosmological models suggest that under the right conditions, quantum fluctuations inside an otherwise empty vacuum might trigger the birth of a new expanding region of space. From the inside, that region could resemble another Big Bang, not exploding into pre-existing space, but creating new space as it expands. Remarkably, this resembles how our own universe appears to have begun. The Big Bang is often misunderstood as an explosion occurring somewhere inside empty space. Instead, space itself expanded. Every galaxy moved away because space between them grew. There was no center, no edge, only expansion. If another cosmic beginning were ever possible, it might unfold in much the same way. Not inside our universe like a firework, but as an entirely new region with its own space, its own time, and perhaps even its own physical laws. To any hypothetical observers inside that newborn universe, everything would appear astonishingly familiar. A hot beginning, rapid expansion, the formation of particles, then atoms, stars, galaxies, perhaps planets, perhaps life, perhaps curious beings asking where everything came from. They might never realize their universe emerged from the quantum vacuum of another unimaginably older cosmos. Of course, all of this depends upon assumptions that remain deeply uncertain. We do not yet know the true nature of dark energy. We do not know whether the vacuum of our universe is absolutely stable. We do not know whether inflation, the rapid expansion believed to have occurred shortly after the Big Bang, can begin again under natural conditions. And perhaps most importantly, we do not know whether our universe is only one among many. This brings us to one of cosmology's boldest ideas, the multiverse. The word itself sounds like science fiction. Yet within physics, it refers not to a single theory, but to an entire family of hypotheses. Some versions suggest that countless universes may exist, each with different properties. Others propose that new universes continuously emerge through processes connected to inflation. Still others imagine reality as an endless cosmic landscape where different regions settle into different physical laws. At present, none of these ideas has been directly verified. They remain fascinating possibilities rather than established scientific facts. That distinction is important. Science grows stronger not by pretending certainty exists where it does not, but by carefully separating observation from imagination. Even so, these ideas invite an extraordinary thought. Perhaps what we call the universe is only one chapter in a much larger story. Perhaps beginnings and endings are local events. One universe grows old, while another is just being born. One sky fades into darkness, while another fills with its very first stars. In such a picture, creation is not a unique event. It becomes an ongoing process unfolding across realities forever beyond each other's horizons. There is another possibility, equally mysterious. Perhaps nothing new ever appears. Perhaps our universe continues expanding forever, becoming colder and emptier without end. No rebirth, no second beginning, just infinite silence. Oddly enough, infinity has a way of making both possibilities feel strangely similar. Whether something eventually happens after unimaginable spans of time, or whether nothing ever happens again, both futures lie so far beyond human experience that they almost merge into the same mystery. Our minds evolved to understand tomorrow. Perhaps next year, perhaps the next century. They were never designed to grasp futures extending across numbers with millions of digits. And yet, we try. There is something profoundly human about asking questions we may never answer. When our ancestors first looked upward, they wondered whether the stars were tiny fires, distant worlds, or holes in a great celestial dome. Today we know they are nuclear furnaces scattered across galaxies billions of light years away. Questions once thought impossible gradually became ordinary knowledge. Perhaps future generations, if any remain during the age when galaxies still shine, will solve mysteries that today seem forever beyond our reach. Or perhaps some questions truly lie beyond observation. Not because they lack answers, but because the universe itself prevents anyone from witnessing them. If another Big Bang someday blossoms from an empty vacuum, who would remain to see it? No civilization from our universe could survive long enough. No message could cross between separate expanding universes. No historian could record the transition. The greatest event imaginable might occur in complete solitude. A new cosmos awakening without applause, without witnesses, without memory of the universe that came before. There is a certain poetry in that possibility. Flowers bloom in forests where no one walks. Stars form inside clouds that no civilization will ever discover. Entire galaxies live and die beyond the observable horizon, forever unseen. Nature has never required an audience in order to create beauty. Perhaps universes are no different. And perhaps that is the quiet lesson hidden at the end of our journey. Existence is not valuable because someone observes it. The stars burned for billions of years before eyes evolved to admire them. Galaxies danced long before minds learned mathematics. The universe has always been astonishingly creative, whether or not anyone was watching. As our own story reaches its final pages, we are left not with certainty, but with wonder. Maybe the universe ends in everlasting silence. Maybe quantum fluctuations eventually light another cosmic dawn. Maybe countless universes rise and fade, like waves upon an endless ocean whose true shoreline no equation has yet discovered. We simply do not know. And perhaps that uncertainty is the most honest ending of all. For every answer science has uncovered, it has revealed even larger questions waiting beyond. Every horizon reached uncovers another horizon farther away. The universe has never stopped surprising us. Perhaps it never will. So as this final silence settles across the cosmos, After every star, every galaxy, every black hole, and perhaps every atom has disappeared, we are left with one last question echoing through eternity. Not whether the universe will end, but whether endings themselves are simply beginnings that no one remains to witness. Perhaps somewhere beyond time, beyond space, beyond every map our mathematics can currently draw, another first sunrise is already waiting to happen. And if it does, it will rise exactly as ours once did. Quietly, patiently, without announcing itself, beginning another story that, for a while at least, will once again fill the darkness with light. 16. The final silence before a new beginning. For nearly 14 billion years, the universe has been telling one continuous story. A story that began in unimaginable heat. A story that gave birth to stars, galaxies, planets, oceans, mountains, forests, and eventually minds capable of wondering where they came from. Tonight, we've followed that story almost to its final page. We've watched stars exhaust their fuel, galaxies fall silent, black holes slowly evaporate into nothingness. Even atoms themselves may eventually surrender to time. By every measure we understand today, the universe appears destined for an ending unlike any story humanity has ever imagined. Not with a dramatic finale, but with an almost perfect stillness. And yet, science has taught us something remarkable over the past century. Every time we believed we had reached the ultimate answer, nature quietly revealed another layer beneath it. Perhaps the greatest surprise still waits beyond the horizon. Because when physicists ask what happens after the heat death of the universe, an unexpected realization appears. The honest answer is, no one truly knows. Heat death describes what happens if the universe continues expanding forever, while the laws of physics remain exactly as we understand them today. It is the most widely accepted long-term prediction because every observation currently points toward accelerating cosmic expansion. But science never promises certainty. It only follows evidence as far as evidence allows. Beyond trillions upon trillions of years, our equations begin entering territory no experiment could ever test. Gravity behaves strangely. Quantum mechanics becomes increasingly important. Time itself may no longer resemble the familiar flow we experience every day. The farther we travel into the future, the less confident our predictions become. And somewhere beyond those uncertainties, extraordinary possibilities begin to emerge. One of the oldest ideas is that the universe may somehow be cyclical. Instead of one beginning followed by one ending, perhaps there have been countless beginnings. Imagine breathing. You inhale, you exhale. Neither motion exists without the other. Some physicists have wondered whether the cosmos itself might behave similarly on unimaginable timescales. Expansion, contraction, expansion again. Long before the discovery of dark energy, many scientists expected gravity might eventually overcome expansion, pulling every galaxy back together. In that picture, the universe would end in something called the Big Crunch. Galaxies would rush toward one another. Background radiation would grow hotter. Space itself would shrink. Eventually, everything could collapse into conditions resembling those that existed near the beginning. Could such a collapse trigger another Big Bang? It is a beautiful idea. Elegant, symmetrical, almost poetic. Unfortunately, current observations suggest this is unlikely. Dark energy appears to be pushing galaxies apart faster over time, making a future collapse increasingly difficult. Instead of reversing, expansion seems destined to continue forever. Yet even that may not be the whole story. Dark energy remains one of the greatest mysteries in modern physics. We know it exists because we observe its effects. We do not know what it actually is. If its behavior changes over unimaginable spans of time, the universe's future could change with it. Another possibility emerges from quantum mechanics. In everyday life, empty space appears to contain absolutely nothing. But quantum physics paints a very different picture. Vacuum is never truly empty. Invisible fields constantly fluctuate. Particles briefly appear and disappear. Energy ripples through what seems like perfect nothingness. The emptiest regions of space are, paradoxically, alive with microscopic activity. Some cosmologists wonder whether these fluctuations could occasionally become far more dramatic. Given enough time, could an entirely new universe emerge from what appears to be empty space? Remarkably, some mathematical models suggest this may not be impossible. Our own universe might itself have originated from an incredibly rare quantum event. If so, perhaps creation is not a singular occurrence. Perhaps universes occasionally bloom like tiny bubbles within an unimaginably larger cosmic ocean. Each bubble would possess its own laws, its own galaxies, its own history, its own observers looking into their own night skies. If that picture is correct, then endings become strangely relative. One universe grows old while another is being born. Another possibility takes us even deeper into mystery. Some theories suggest our universe may be only one region within an endless multiverse. Imagine standing in a vast forest where every tree represents an entire cosmos. Some trees are young, others ancient. Some are flourishing, others have already fallen. No observer living within one tree could ever see the entire forest. Likewise, we may forever remain unable to observe realities beyond our own cosmic horizon. Not because they do not exist, but because the distances separating them exceed anything light could ever cross. These ideas remain speculative. There is currently no direct evidence proving the existence of multiple universes, yet they arise naturally from several attempts to unite quantum mechanics with cosmology. Science allows them to be explored, not because they are proven, but because they are mathematically plausible. Perhaps the most profound possibility is simpler than all of these. Maybe our understanding of time itself is incomplete. We naturally imagine time flowing like a river, past behind us, future ahead. Birth, growth, death, end. But modern physics has repeatedly challenged common intuition. In Einstein's relativity, time behaves differently depending upon motion and gravity. There is no universal cosmic clock ticking identically everywhere. Some physicists even propose that time may not be fundamental at all. Instead, it could emerge from deeper relationships among space, energy, and information. If time itself is an emergent phenomenon, then asking what happens after the universe ends may be similar to asking what lies north of the North Pole. The question itself might require a different framework. Perhaps beginnings and endings are concepts meaningful only inside our universe. Outside that context, they may simply lose their meaning. As strange as these possibilities sound, history reminds us to remain humble. Only 100 years ago, many scientists believed our galaxy contained the entire universe. Then, Edwin Hubble revealed countless galaxies beyond the Milky Way. Later, astronomers discovered the cosmic microwave background, then dark matter, then dark energy. Each discovery expanded reality beyond what anyone previously imagined. Who can say what discoveries await civilizations millions or billions of years from now? If intelligent life continues somewhere in the cosmos, their understanding of physics may surpass ours as profoundly as ours surpasses ancient astronomy. Questions we consider impossible today may someday become straightforward, or entirely new mysteries may replace them. Curiosity itself may never end, and perhaps that is the most beautiful conclusion of all. Throughout this journey across cosmic time, one pattern has quietly repeated. Stars ended, yet new stars formed. Galaxies collided, yet larger galaxies emerged. Black holes destroyed matter, yet helped shape entire galaxies. Even apparent destruction often became the beginning of something unexpected. Nature rarely wastes an ending. Transformation seems woven into every level of existence. The atoms inside your body were forged inside stars that died billions of years before Earth existed. Their endings became our beginning. The calcium in your bones, the oxygen you breathe, the iron flowing through your blood. Every one of them is ancient stardust, continuing a story far older than humanity. Perhaps the universe itself follows a similar rhythm. Perhaps not. We simply do not know. And there is something deeply comforting about that uncertainty. Mystery is not failure. It is the horizon that keeps exploration alive. If every question already possessed an answer, curiosity would disappear. Instead, every generation inherits the unfinished map of reality, adding a few more pieces before passing it onward. For now, our best evidence suggests the universe will continue expanding into colder, darker, quieter ages. The stars will gradually disappear. Galaxies will drift beyond one another's horizons. Black holes will evaporate. Matter itself may eventually dissolve. An almost unimaginable silence may stretch across eternity. Yet somewhere beyond the limits of today's knowledge, another chapter could already be waiting. Whether the universe experiences one final ending or countless new beginnings, we remain privileged to exist during one extraordinarily brief moment when stars still shine, galaxies still sparkle across the night sky, and conscious beings can pause long enough to wonder why any of it exists at all. That simple act of wondering may be one of the rarest events the cosmos has ever produced. Perhaps that is reason enough to look upward with gratitude. The universe has given us no promise that its story lasts forever. But it has given us this moment, this sky, this quiet evening beneath the stars. And sometimes, that is more than enough. Thank you for spending this peaceful journey through cosmic time with us. If you'd like to continue exploring the universe, one quiet story at a time, don't forget to subscribe. And until our next voyage, sleep well beneath the stars.